Got it. That's good. Those participation points were in jeopardy there for a second. I don't know. I have high standards for camera work. You know? Not really. Hey. Nobody wants to see that. No offense. But okay. Anyway, I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Thank you for these students, most of them, and I pray that you'd help us to have a good day today to glorify you, what we do, Lord. In your name I pray. Amen. Well, I know you guys are itching. You're just eager with anticipation for the quiz, right? So the quiz is take-home, of course. And, I mean, not of course. I mean, who gives a take-home quiz, right? I do. And as to not punish the honest people, you are allowed to work together on that. So, you know, when I give it to you, you can start working on it. So that should happen today at some point. So here's another example. Any questions before I dive into a few more examples of applications of first-order problems? Just to review, at this point, I have shared with you guys the major solution techniques for first-order differential equations, in particular separation of variables, the method of exact equations, the integrating factor method, substitutions, right? And that's been pretty much it. We've discussed also the connection of, vector fields and the problem of finding integral curves. I've shared with you two different ways, to try to find it parametrically to solve the system of differential equations, which corresponds to finding the path. We actually did that, I think day one. And then alternatively, you can solve the, eliminate time at the level of calculus, solve dy dx equals, what was it, p over q or q over p? I can't remember, but you can look back, right? So we found two different ways to find integral curves day one, so we did that. We discussed what a conservative vector field was, the connection of that to exact equations, right? And I think that's a pretty good summary of what we've done so far, right? So today I'll say a little bit more about first order problems, and then pretty soon we're going to start the nth order material and go on, okay? A couple of things left to do. I need to show you a couple more examples, and I should also at least carefully state the existence and uniqueness theorem for the first order problem. I'm not going to prove it or anything like that, but I should at least state it for you so you have some sense of why what we're doing seems to always work, all right? Any questions? Okay. So here's a problem. Suppose the force of friction on a speeding car, this is my example 2.59, it's a good example. Suppose the force of friction on a car with mass m is minus bv squared, right? Where b is greater than 0, positive is constant. It's a constant. On car with mass m with initial velocity v naught and position. So we're thinking about one-dimensional motion here, all right? So we're just car, straight line motion. It's got a friction force which is proportional to minus the velocity squared. And I have two questions. The one is to find the velocity as a function of time, and the other is to find the velocity as a function of position, all right? Right, in other words, find v equals to v of t, and for part B, we want to find v as a function of x, if you'll allow me to abuse notation. The abuse of the notation, of course, is that technically speaking, there are two different functions going on here. Like there's f of t, and maybe there's like a g of x. And they're related, but they're not the same quote-unquote function, right? To be more mathy here for a second. Anyway, let's get to it. So this is a physics problem, and we're assuming that the net force on the car is the force of friction, right? So what we have then is we have that the mass times the acceleration is equal to minus bv squared. This is Newton's second law, right? But this is also a differential equation. So in particular, we have m dv dt equals to minus bv squared. Okay, great. Now, I can do what to solve this? If I want to find v as a function of time, all I got to do is separate and integrate. So, and be smart about your separation and your integration. So we got dv over, let me suggest putting that minus here because that's ever so lovely for the integration. And that's going to be equal to b over m dt, I think. Right? Now, here's a trick. When you're given initial conditions, you can build them into the integration, right? Like what we're doing when we separate and integrate is using the substitution theorem for integration, right? Which says that you have to change the bounds, among other things. So the application of that here to make our life as easy as possible is to integrate, say, from v0 to vf, right? And to integrate from, say, t0 to tf. In other words, integrate from the initial to the final time, integrate from the initial to the final velocity. The U substitution says we have to match the bounds like this. That's what the theorem of calculus says. And then what's the antiderivative of minus 1 over v squared? Just 1 over v, right? So evaluated from v naught to vf is equal to b over m times the change in t, tf minus t naught. So in short, we have 1 over vf minus 1 over v naught is equal to b over m times tf minus t naught, right? So if we set, let vf equal to the velocity at time t and let t naught equals to 0, then what is that? That gives us the nicer formulas. 1 over v minus 1 over v naught equals b over m times t. I mean, it's my custom. When I talk about initial velocity or initial, position, I'm usually thinking time 0 for that. But strictly speaking, the usage of the term initial condition, that doesn't have to be given at time 0. It could be given at some other time. If I gave you the position and velocity at time 3, that would still be a set of initial conditions. That's the meaning of, that's the language that's used in differential equations, right? So initial doesn't have to mean time 0. But it could, and I usually think of that as the default. And so algebra, 1 over v equals to 1 over v naught plus b t over m. And then we solve, we get v is equal to 1 over v naught plus bt over m. And then I think I like to simplify this a little bit. This is v is equal to v naught over 1 plus bt v naught over m. I think that's a nice formula here for part A. Now, I projected this solution and talked about it the other day, but I thought it would be wise for us to work through it step by step, yeah? Agree, disagree? Okay, well, anyway. I said, I mentioned if we take time going to infinity, we get the velocity going to 0, right? I think it kind of makes sense, yeah? So that was part A. To solve part B, we used the v dx trick. So for part B, we've got ma is equal to minus bv squared. But we should look at that as m dv dt equals m dv, dx dt, dv dx. In other words, v dv dx, which is super nice because we've eliminated time at the level of the differential equation, which means to find the velocity as a function of position, I don't have to do the more horrible thing, which would be to find the position as a function of time, solve that formula for time as a function of position, and then plug it into what we just found. That would be the other way to do this. It's so much better to just find the differential equation, which allows you to find velocity as a function of position directly from Newton's equation, as opposed to doing a couple algebra steps. You understand what I'm saying? You could, in principle, say that this is equal to dx dt, right? You could then integrate this equation. That would give you x as a function of time. You could then take that equation and solve it for t as a function of x. You then take that t of x and you plug it back into here. That would give you the velocity as a function of position. What I'm about to do is way easier than what I just said. See, we've already eliminated time at the level of calculus right here. That's a timeless differential equation. It's just an equation in v and x, which is what we want. And then separate and integrate. So we're off to the races here. Let's see here. We've got v dv over v squared. I'll leave the minus over on the other side this time. Minus b over m dx. Looks like that's dv over v equals to minus b over m dx. Let's use my build the initial conditions into the integration idea again to make our life easier. So instead of just integrating both sides and then adding a constant, I'm going to integrate both sides conscientiously using my initial data, v naught to vf. And over here I'm integrating from x naught to xf. The vf and the xf, these are placeholders. I'm going to get rid of them after the next step. I can't put v and x at the top of those bounds because that would be an abusive notation in the sense that we shouldn't write the bound of the integral being the same as the variable of the integral, right? That's a no-no. Some of you will do it and not get confused somehow nevertheless, but we shouldn't do it. Natural log the absolute value of v evaluated from v naught to vf is equal to minus b over m. Well, this integral works out to xf minus x naught, right? So in other words, the natural log of the absolute value of vf minus the natural log of the absolute value of v naught is equal to minus b over m xf minus x naught. You notice that I have no constant, right? I mean, the constants that I'm dealing with are the initial conditions that were given. So I'm building the initial conditions into the solution by integrating in this way. Now, you guys know this is the natural log of the quotient of vf by v naught, yeah? And that's equal to minus b over m xf minus x naught. Just a little algebra there for you. And so we can exponentiate both sides, and we get that, well, vf over v naught is equal to, well, the absolute value of vf over v naught is equal to e to the minus b over m xf minus x naught, yeah? Exponentiating both sides. So let's go ahead and set vf equal to v and xf equal to x, and that will give us what we're after, which is that v over, well, it's almost what we're after. The absolute value of v over v naught is equal to e, bless you, minus b over m x minus x naught, like so. Now, what's that say? I mean, we can erase the absolute value and do what? Put a plus or minus on one side or the other, yeah? Let's put it over there. Now let's think about that. So v is equal to plus or minus v naught e to the minus b over m times x minus x naught. So my question, if we set x equals to x naught, what does this reveal? About the plus minus. What is the meaning of v naught as it relates to x naught? What is v of x naught equal to? How are these connected? I mean, we're saying V of x naught is equal to what? V naught, right? By assumption. So if I put x equal to x naught, what happens here? I get
1.
e to the 0, which is 1, right? So I get V of x naught is equal to plus or minus V naught, e to the 0, right? So what can you conclude about the plus or minus? We must choose plus. Very good. And that plus, it could very well mean that the velocity is negative. I mean, V naught could be negative, right? So that plus is not, just because I write V is equal to V naught e to the minus b over m x minus x naught, that doesn't necessarily mean that the motion is to the right. It could be to the right or to the left, because that V naught could be positive or negative. And there you go. That is the velocity as a function of position. Any questions? Yeah. Good question. I suppose if the velocity was 0, then if V naught 0, I think then the solution would just be the velocity stays 0, right? I mean, just physically speaking, that seems intuitive. And again, it's kind of funny, right? Here, we recover that, right? If you put V naught equal to 0, then this formula still says the velocity just stays 0 for all. I mean, well, also x is equal to x naught in that case, right? So that if we were to find position as a function of time, it would also just stay at its initial position. So, but yeah, that would be an extraneous case. Other questions? Yeah.
So getting rid of the minus sign or selecting the positive, it didn't mean that that solution has to be positive. It just means that they don't have an inverse relationship.
It means that if I'm going to write the solution in terms of the initial velocity, it's not up for grabs. I have to put plus V naught here. It would not be logical to put minus V naught, because then I would not get that the velocity at position x naught is equal to V naught, which it's supposed to be. So, but yeah, I mean, pragmatically speaking, given an actual physical situation, that could be a negative or a positive number, or it could be 0. This is a trick we get sucked into sometimes. Like, you guys see a constant, and then you see like a minus in front of it, and like people will think that minus the constant has to be negative. Right? But you forget that the constant itself could have a sign in it, right? And this is a common confusion. I have entered this confusion myself many times, and when you do, it's a bad place. It's hard to get out of. And once you realize it's what was confusing you, you're like, it's the worst. It's the worst. All right, another example. How about that? Here's an example for you. Electrical engineering types. So suppose you have a, battery, voltage source with voltage E, and you've got a resistor R, and you've got an inductor with L. Then Kirchhoff's voltage law says that the voltage source minus I times R minus L di dt is equal to 0. So that's Kirchhoff's voltage law. Now, when you take Physics 232, you should learn how to figure out initial conditions depending on whether or not switches are opened or closed, right? So let's go through the thought process there. Let's suppose that before time 0, we've got like a little switch, yeah? Now, this is not the kind of thing I'd test on, because this is a Physics 232 a prerequisite for this class? No, Physics 231 is a prerequisite for this class. So, motion problems, energy problems, completely within my fair domain, right? A circuit problem, That would just be mean, right? So I will show it as an example in class because some subset of you are electricals, or actually most of you are engineers. And for an engineer to not be interested in an RL circuit is shameful. It's shameful. Every engineer should at least take ownership of the basic thing of other engineering fields. To not assume this is part of your province is to not be a proper engineer. You should take more pride in what you do. There's a certain arrogance that comes with being an engineer. If you do not embrace this arrogance, you will not be respected. I'm sorry, but these things are true. I was once at a school with thousands of engineers. I know how they behave. All right, I probably need to edit that out, but no, I love engineers. They solve problems, you know, and they do care about details often. Okay, so this is Kirchhoff's voltage law, or KVL. It says that the energy that's developed by the voltage source is then lost as it vibrates atoms in the resistor to drop the voltage according to Ohm's law, which is IR. And then it also takes energy to build up the magnetic field inside this inductor, right? That's what this term is about. As the current changes, the voltage builds up over the inductor until finally it reaches some steady state, at which point there's all the energy that you're going to get in the inductor. So like the shorthand of it is that when you first close that switch, the current's 0, all right? And because the inductor is going to resist an instantaneous change in current. That's the story. So the current will initially be 0 when we close the switch because the inductor resists an instantaneous change in current. But after a long time, after the magnetic field in the inductor is completely built up, the inductor behaves like a short circuit. So after a long, long time, we expect that the current it's going to be like this isn't even here. It's just like a wire after you close the switch. And we know that the long-term current should just be E over R by Ohm's law. Okay? Now, if you don't know what I'm talking about, that's okay. But this is closed at time 0 plus. Just a little bit after time 0, we close the switch, okay? So what I'm trying to tell you is that through physical reasoning, the initial current is 0. All right? So that's our initial condition. This is a differential equation. E here is given to be a constant. It could be 9 volts, right? The resistance could be 13 ohms. The inductor could be 47 henries, although that would be a really big inductor. My sister-in-law thinks it's hilarious, absolutely hilarious, that the units for inductance are henries. She thinks it's a very funny unit. What do you guys, strike any of you as funny? She's the only person I've ever met who finds this to be funny. But, she thinks it's very funny. I don't know. You guys are like, just give me my quiz. Fine. I'll go on. You guys are no fun. All right, so what is this? Let's get to it. This is di dt. And you tell me why I'm doing what I'm doing. Di dt, I guess in between step here. This is L d. I'm going to do this step here because it'll help me not make a stupid mistake. Plus IR equals to what? E, yeah? So I'm just saying that the current, that the voltage supplied to the circuit is equal to the voltage dropped is another way to look at that. And then I can divide by L. So I got di dt plus R over L times I is equal to E over L. The reason I did that was to put this into what? Standard form. Now we have a linear differential equation in standard form, and we know how to solve this by the integrating factor method, right? So what's the integrating factor? Probably I should not call the integrating factor here I. That might be a bad choice, right? As a different meaning. So since we've already used I, we'll use mu for the integrating factor. It's going to be the exponential of the integral of R over L times t. Oh, well, dt rather. Which in other words is e to the RT over L. Now, traditionally that is written as e to the t over tau, where tau is equal to L over R. This has a name, it's called the time constant. The time constant for an RL circuit is L over R. And it has units of time. Anyway, multiply this. We've got e to the R over L t times di dt plus R over L e to the R over L. See, if I'd been writing tau, think of all the R's over L's I wouldn't have had to write, but it's too late. E over L e to the R over L t. Now, if I did this right, we should be able to do the, what? Reverse product rule, right? And I think that's the case, yeah? This is d dt of what? d dt of e to the R over L times t times I, and that's equal to the voltage divided by the inductance times the exponential of t over the, RT over L. Let me use a kind of similar trick to the one I did already. Let's integrate, but let's integrate smart. Let's integrate from, say, time 0 to time final, right? From t0 to tf, what's that going to do? But let's let t0 be the, here, I'll get it eventually here. Integrate from, say, from time 0 to a final time, all right? And dt. And integrate over here from time 0 to a final time. So the right-hand side, that's e over L. By the chain rule, L over R, e to the R t over L, evaluated from time 0 to time final. The L's cancel. We have e over R, e to the R final time, tf, over L minus 1. And then on the other side, we can use the net change theorem, right? Because we've got, what is this? This is e to the R tf over L I of tf minus e to the R, I'll get out of the way here in a second, 0 I of 0, okay, by the net change theorem. Now that has to be equal to the integration I just did. But what's I of 0? Don't tell the other math professors I did that. Okay. Actually, they won't care. No one cares. That's 0. By physical considerations, and this is what we're after. So now we can say set t equals to tf after the integration, right? And that will give me I of t equals to, I'm going to multiply by e to the minus RT over L to solve for the I. So in total, the current, as a function of time, right, is E over R times 1 minus e to the, minus RT over L. Of course, we could rewrite, this term here is actually e to the minus t over tau, right? And there you go, that's the current as a function of time for this RL circuit, for the charging inductor, as it's called. So being able to apply the method of integrating factors means you can solve like RL circuit problems. Now, if you wanted to solve an RLC circuit problem, a resistor, an inductor, and a capacitor, we don't quite have the math for that yet. We'll be having the mathematics for that we'll pick up here in about 2 weeks or so, because that's a second order problem. You could also solve the charging capacitor problem. That's also a first order differential equation, except in charge and time as opposed to current and time. Now let's check. Does this actually match the features that I claimed? What happens as time goes to infinity? what happens to the exponential term? It's gone, right? It goes to 0. In fact, the time constant, after about 5 time constants, this term is about 0.01. After 1 time constant, it's only about 0.67. After 2 time constants, it's only about 0.3. So like it's an exponential. It drops off pretty fast. After 5 time constants is essentially irrelevant. So the time in which this circuit is dynamic is about 5 time constants. 5 time constants is the lifetime of this circuit in terms of it being interesting. After 5 time constants, it's essentially a DC circuit where the current is just E over R. But at time 0, what happens? At time 0, the exponential is 1, and we get 1 minus 1, which is 0. It gives us back that initial current of 0. So anyway, my larger point to you is to solve circuit problems, you need to understand how to solve differential equations, right? I mean, at least to understand AC circuit analysis, it's all differential equations. Like, I can use phasors. Well, good for you. Maybe I'll put that in your second quiz. Yeah? No? You're like, that's okay. We'll do without it. Any questions? No? All right, well, one other thing to nail down today, and then I'll give you the quiz and talk about it for a little bit. But I think today is probably a pretty good time to talk about energy analysis. So let's go ahead and try to put that notch in our belt, so to speak. What is energy analysis? Ooh, probably shouldn't have erased that, but too late. So here's the idea of energy analysis. So we're thinking of the net force being equal to minus the potential energy differentiated with respect to time. So it's a one-dimensional problem. We've got a potential energy function. Minus the derivative of that gives us the net force. This is a conservative system, right? So if you look at that situation, Newton's second law says that the mass times the acceleration is equal to the net force, right? But that's also equal to minus du dx. Okay, great. Well, then that means that m dv dt plus du dx is equal to what? Well, it's equal to 0, isn't it? A neat trick that's often successful in junior level classical mechanics, you go take the course here and you'll find out. You might have that course in the engineering department. I don't know, maybe you guys do this. But multiply by x dot, as it's called, which for us, I'll just write it out, dx dt. If we multiply by dx dt, the equation above, what we've got is we've got m dx dt times dv dt, yeah, plus dx dt du dx equal to 0. At which point you can tilt your head and squint and see, aha, this is du dt, right, by the chain rule. And this guy, well, that's d dt of m over 2 v squared. That's actually if you look at the differentiate m over 2 times v squared, well, you'll get, 2v dv dt times 1/2, which is exactly what I have above there. So that's just an identity of calculus. And so what I'm saying is this equation really just implies that the total derivative of 1/2 mv squared plus u is equal to 0. Now, I derived this in 3 dimensions about a week ago, right? So I'm just showing you a one-dimensional derivation of the fact that if we have a conservative force, we have conservation of energy. In fact, the thing I just put in brackets is called the mechanical energy of the system, right? This is mechanical energy. So it's the energy, this is u actually as a function of x. So we're looking at E, which is a function of, x and v. Mechanical energy is conserved along where? people, physicists will say something like, it's conserved along the equations of motion. What are the equations of motion? That's just a fancy way of saying where Newton's law holds, energy is conserved. Okay. This is very interesting because it means that to understand motion for a conservative system, we can trade the problem of finding position as a function of time, which is, something we might be able to do. Finding position as a function of time, what's that mean? That means you got to solve this equation here, which is what? M d squared x dt squared, yeah? So you got to solve m d squared x dt squared equals to the net force. This net force could be all kinds of crazy junk, right? I mean, the net force could be something as cranky as like a cubic or whatever in x. I mean, it could be all kinds of stuff where we don't really have a nice solution technique for solving this differential equation. Yet, we can still think about energy and understand the motion of the problem in terms of the position velocity plane, the so-called Poincare plane. So the Poincare plane sometimes it seems like it's called phase plane. Certain quarters. It looks like this. What we do is we plot the velocity this way, we plot the position that way, and you can plot possible motions as level curves of the energy. See, because this says that energy is conserved, right? Energy is equal to constant on the equation of motion. And there's more than you can say than that, right? What else can we say here? If you think about the meaning of V and X, there's a lot of fine, there's a lot of strings attached here, right? Energy is equal to 1/2 mv squared plus the potential energy. That's one thing, but there's more than that. The velocity actually for us is equal to dx dt, right? So if you think about that, there's two cases. What's that mean? That means that your rightward for v greater than 0, and your leftward for, well, not between 3 and 6, but for v less than 0. So, sorry, still sore point? No. I feel bad for the people going right between 3 and 6 now, out on words. Because now, like, everybody's going right? I wonder what the percentage of increase in U-turn at the gas station is. I mean, we're talking about 300%, 500, 1,000%. What kind of percent?
Do you know what the rationale behind that is? Is it helpful? Is it very helpful?
Well,
I think what it was people kept running the red light and blocking up people going the wrong way. Or trying to go.
Yeah, people would always clock the intersection going, like, coming from north, I guess, going left.
I don't know. I got stuck in that line once, and I decided I was never parking at the parking garage again. So, anyway. Well, I'm glad you guys understand. Whatever. Good. So the larger point here is that since velocity has the meaning it does as it relates to position, these energy level plots, they're not just like any old level curves. They come with this particular string attached. They have to go to the right for positive velocity. They have to go to the left for negative velocity. This is actually very, very, limiting as to the possible shapes that are allowed. Just to give you a specific example of this, we'll put the mass equals to 1 because it's not fun to have mass not equal to 1. And we'll let the potential energy equal to, I don't know, what's a good one to start with is x squared, right? That's the potential energy for a spring, right? So that if that's the potential energy, that would say that the net force is what? Minus 2x, right? That's Hooke's law, right? So, you know, if I draw, oh, and see, I've made myself a mess. I need to do this best. I should draw the potential energy graph right under here is my custom. So if we draw the potential energy down here, the potential energy plot, then that's x squared. So it looks something like this, right? And fine, E 1/2 mv squared plus the potential energy, right? Generically speaking, but it's x squared here. Now that's going to be constant. So if I, you know, do something like, say, look at this energy level, right? The reason that I just draw it here, let's say that's E1, I can't go past the potential energy, because to go past that would be to say that the kinetic energy, the 1/2 mv squared, was negative. See, because the net energy is kinetic energy plus potential energy, right? And so if the net energy is over the potential energy diagram, that means that the net kinetic energy is negative. But that's impossible because kinetic energy is positive by construction. So motions which are physically allowed have to have energy which is larger than, or at worst equal to, the potential energy. What happens when all of the energy is potential? That means the kinetic energy is 0, which means that your particles come to a stop, right? And so those just have the meaning of intersecting the x-axis in this graph above. Okay? So I get this point, I get this point, and then, like, if you think about energy E1, what happens when x is equal to 0? Well, there, your kinetic energy is this big, right? Kinetic energy is this big when we're at x equal to 0. We have the biggest kinetic energy at x equals to 0. Just like with spring, is going fastest when it passes through its equilibrium, right? Stretching or compressing. And so, long story short, that gives us something like this. And that would be the energy for E1. That's the E1 energy plot. Now, and then you can start thinking about other energies, right? Like, I should have done that in red. Stink. I'll fix it. Or, let's see, I'll do one in green. Or you could have E2, like this, yeah? There's turning points, something like that. And so I can add more though, right? Because these are actually parametrized curves. They go to the right for V positive. They go to the left for V negative, as I was saying. So the complete picture is something like this. I mean, above, let's see here. Above the x-axis is the string, is the spring stretching out, right? Below the x-axis is the spring rather compressing, right? And as it goes in this cycle, and that's the motion. I've done all of that without actually solving the to solve the differential equation directly would be what? I'd have to solve d squared x dt squared equals to what? Minus 2x. I'd have to solve this differential equation. If I could solve that, then I would find x as a function of time. That would describe the motion, right? But I didn't have to do that. I can look at the energy, the velocity position plane, and understand the motion of a spring without actually solving that differential equation. A spring is simple enough. We're going to solve that differential equation in about a week or two. Right? It's not a big deal, but it could be much worse, all right? Like, we could have something much worse. Let me do one that's worse. I won't even try to conjure up a formula for it. I'm just going to give us a somewhat unpleasant, potential energy diagram. So suppose we're given a potential energy that looks like this. Whee! All right, something like that. And then what I want to do is plot the phase plane, the Poincare plane for this. given potential energy. So this here is u of I'm plotting u of x here. Now, so when I ask this question, I try to give you guys energy levels. Otherwise, it's just a complete drudgery to grade. So typically, I will say, plot the energy levels for these given energy levels. It makes my grading not so nuts. So let's suppose that the given energy levels are like here: E naught, E1, E2, and E3. So I'll start with E naught. If we look at E naught, the dotted line, the dots I'm making right here, these are classically forbidden motions because the potential energy is larger than the net energy, right? Actually, one of the interesting things in quantum mechanics is that there's something called tunneling, where you essentially, in some sense, have negative kinetic energy. You're allowed to go into the classically forbidden region. And this is not just a quirk of quantum mechanics. It's actually kind of the part that makes semiconductors make sense in terms of what's called band gap theory and so forth. Anyway, that's another story entirely. But this tunneling is actually important to semiconductor physics. My point here, though, for you guys, is just that it is forbidden until we get to right about here. And then we've got E naught, yeah? So if I'm careful, that's about right here. That's the stopping point. And so what we got is just, this is the trajectory. It's coming in to the right, it hits this point, and then it goes back out. And that's all we can see for E naught. For E1, forbidden, 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 forbidden. It's debatable, depending on how you interpreted my graph, okay? But forbidden, 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 it is allowed. Forbidden, 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 it is allowed. Okay, so here, it depends on where you start. So apparently, I think this is the last voyage of this marker. So we've got this kind of over here, like that. And here we've got a little trine, like that. And those are the E1 motions possible. Now, where you are, right? Where you are will depend on what? It'll depend on where you start, right? If you start in this potential well with an energy E1, you're going to stay there. You're just going to bounce back and forth there, right? Like some people are born in Lynchburg and, some of you were born elsewhere and you come to school here, you get over this hump, and then you graduate with about this much energy, and then just like that. I know, because you guys come up to me like 10 years later, like, hey, Dr. Cook, what's going on? Remember, I had calculus with you, and like 10 years ago? I'm like, yeah, yay. Don't remember. And you people look different 10 years from now. I look more or less the same. I mean, I might be fatter or something, I don't know, but you guys look different 10 years from now, I tell you what. All right. My guys, you change your last names, get married, all this kind of stuff. It's annoying. All right. You should if you come up to me and say, hey, Dr. Cook, you should also have me wearing a name tag, like, I'm such and so forth, from the 2005 offering of, well, that wouldn't be here, 2010 offering of Calculus 3 or something, right? You should but it's kind of a dead giveaway. No one in church is going to call me Dr. Cook unless I would, somebody calls me Dr. Cook, I'm like, oh, that's a student. I didn't know that. I recently learned one of my son is good friends with a kid, and it turns out that his dad took calculus from me, I don't even know, 8 years ago or something. I didn't even realize. I mean, I knew who this kid was. I'd had him in cubbies, blah, 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 blah. It had not dawned on me that this was the child of one of my students. So the trouble is, you guys too many of you stay in Lynchburg. It makes it very disconcerting for me. You should go on. Go out to the world. Live. Don't stay here. I digress. Stay here. It's a lovely place to live. Whatever. All right, fine. Saying get on with it. All right.
Oh, no, that's not. You're good.
Something happened. All right. Anyway, at energy E2, forbidden, 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 allowed. Forbidden, 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 allowed. Forbidden, 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 allowed. And so tracking those points up here, we have like this, we have like that, like that, like that, like that. So we get like this little closed cycle here. There's another closed cycle around that potential well. And there's a off to infinity kind of deal right there. Something like that. And then finally E3, and then I'll give you your quiz and talk about our day. It's time, right? So E3, I was trying to draw so that it just barely hit the top of the potential hill there. So here's my E3. And so this kind of point is funny. So this is what's called an unstable critical point. So the bottom of each well. Oh, that's the other thing I'm forgetting to tell you guys about. You remember critical points? What's a critical point in the motion? It's a motion where what? The velocity is 0. So if you think about it, a critical point in the Poincare plane is going to be a place where where the velocity is 0 and also where potential energy is maximized. Let me say back up for a second here. Where potential energy is maximized, we talk about critical points in the sense of calculus 1, right? If I give you this graph, I say, where are the critical points? You should be able to tell me. That's relative extrema, right? Or possibly points of inflection, but there's none of those on this that I can see. I mean, max, min, those are the critical points, right? It's no accident that those are also what are called critical points to the Poincare plane. They're these stable centers, right? Or there's 2 stable centers and there's 2 unstable critical points. And I'm about to draw energy level that goes through one of those unstable ones. And so it looks something like this. So it's got like a loop here, but that's not actually a stable thing. Like if you started this motion this way, right, what would happen is you'd bounce off there, you'd come back that way, right? And then what happens is you keep going. So the motion's not bounded. Oh, I'm sorry, I'm an idiot. It goes rightward, right? I can't follow my own instructions to the right. Something like that. To the left, to the left. So this is an unstable point. If I start out at that top of the hill and I just give you a little nudge, there's no telling where you're going to end up, right? I mean, you don't have to stay close to the point. On the other hand, if I'm at the bottom of a potential well and I give you a little nudge, you're going to stay close by, right? Those are stable equilibriums, whereas the tops are unstable equilibria. So anyway, that in a nutshell is energy analysis. Yeah.
Is that where, like, orbitals come from, like, for electrons?
Ah. So for electrons, or you're fine. So something like this, the U is equal to something like -1 over R. And so here's R and here's U. Now here, R is the radius, this spherical radius, if you will. And so you can, much of the same mathematics that is good for orbits of planets is also relevant to this because the Coulomb potential is it's a force that's got a inverse reciprocal square, and the force of gravity is the same. So studying orbits of planets is much the same. This is the potential energy. If you put the potential energy to be 0 at infinity, then this is the potential energy formula function for like a hydrogen atom or something like that, up to some choice of constants. So if your energy is 0, you're like parabolic. If your energy is less than 0, you're down here, right, like that. And so what that means is you're bound, your energy is bound. So these energy levels would be, stuck like this. If you can kick the energy above 0, that means you're not bound to the atom anymore, and that electron can fly off into the plasma or whatever. You asked me about p and d orbitals. I think to answer those kinds of questions, we have to have a deeper discussion about solutions to like the Schrodinger equation and wave. Yeah. So, I mean, to solve Schrodinger's equation, it's the kind of thing we're on the cusp of having the tools to do at the end of this course. But it's still a little bit beyond this course. Solving Schrodinger's equation for the spherically symmetric hydrogen atom is a non-trivial thing. I mean, I think Dr. Skambordis has done it in this course in the past, but it would take a couple of solid days of class to do. Like, it's a hard problem. You have to start by starting with like a 3-dimensional PDE, separating variables. There's tricky things involving spherical coordinates. It's involved. But this is the sort of the basic idea behind things. Yeah, much of the same math. Now, I might actually solve the two-body problem at the end of class actually to describe the problem of central forces. You know, when you got a planet orbiting the sun, you know, how do you solve that? So I might have a day where I can do that in here towards the end. But to solve the Schrodinger equation for the hydrogen atom, I'm not sure. I mean, if you keep begging me, you might push me into it, but your classmates may not be happy. Ah, I see. Well, will they do it in there? Will they actually derive it? I wonder. Did they ever explain to you how they know a mole is 6 times 6.0? What is it? 6.023 times 10 to the 23rd? Like, how do we know Avogadro's number is exactly that? Do you know? I don't know either, but Einstein argued it in a paper, one of his papers in 1905. So. What I know is I was very disappointed in my chemistry, like lab TA, that he seemed to be completely disinterested in that question. Like, you're doing everything. It's wall-to-wall, mole, 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 mole. You don't care about why Avogadro's number is 6.023 times 10 to the 23rd? Hey, me not caring, it's fine. That's not my world. That's your world. You should care about why it's that, you know? If it's just a convention, so be it. But man, you ought to be able to explain that if you're a chemist, right? I think. I don't know. I think so. Now, guys, I ran short on time here, so the quiz in its current format, which I'm going to give to you, it's not ideal because I wanted to, I like to put the problem and then have a page of white space and then you can work on there. You don't have to do that because I'm not giving it to you that way. But what I plan to do after class is I'm going to go add white space and post a white space version of this on Blackboard. If you'd rather work on that, you can. If you work in this, I'd ask you that you recopy the problems down when you work them. All right? So it's up to you. Here's those as problems. Now, supposedly you're going to give these back to me Thursday, start of class. Thursday, start of class. Think about Thursday. How is Thursday going to be? Is there even going to exist class Thursday? I sometimes wonder. I'm just going to call an audible on this one and say that you can turn this in next week.